I am your host Rakesh Trivedi, the Chief Strategy and Growth Head for SignOff Semiconductors.
Thanks for inviting me, Rakesh. And thanks for the audience for tuning in.
You were giving me a very interesting analogy about imagining a DFT engineer to that of a doctor.
My chips are my patient. I run some of the tests on that silicon. I can find out what issues or what disease that chip has, and I can either fix that particular chip or I can make sure that those diseases will not appear in the next generation of the chip.
Doesn't it increase this whole cost of manufacturing? And because the testing cost goes up?
Challenge which comes to us as a DFT engineer, and then we have ways and means to make sure that you can reduce the test cost, so that ultimately in the competitive market you are able to sell your chip in a kind of competitive rate.
Hi everyone, welcome back to the Silicon Edge, a podcast series powered by SignOff Semiconductors. I am your host Rakesh, and in our last episode, we explored how DFT acts as a hidden backbone of reliable chip design. Today, we are taking it a step further. We are looking at the exact pipeline of how chip goes from a blueprint to a computer screen to a physical piece of silicon in your smartphones. To walk us through this, I'm joined again by Rohit Patel, Director of Engineering for DFT here at SignOff Semiconductors. Rohit, great to have you back.
Thank you, Rakesh. It's great to be back.
Rohit, uh, in our conversation which we were having yesterday, you were giving me a very interesting analogy about imagining a DFT engineer to that of a doctor. Uh, it was so interesting. I would like you to bring that to the listeners here. What did you mean by that?
Yes, Rakesh. So I have kind of explained this theory to my grandparents and like my father also, those like who are not aware of what exactly DFT is. So I used to tell them, they used to ask me like generally what exactly your profession is. Then I used to tell them I'm a DFT engineer and all. So they were like, it was very difficult to explain them technically what exactly DFT is. So I simply told them I'm a doctor of a chip, and then I explained them the way the normal medical doctor, for the doctor, any human body, whether it's a female, male, or a younger boy or older lady, any human body is just a body for a doctor, and the job for doctor is to run some test on that body, figure out what disease that body has, and then give the medication, prescribe the medication, and get the body repair. So I use the same theory when I'm a DFT engineer. I do the similar thing, but for me, my chips are my patient. So basically, each and every chip does not matter what is the application of that chip. For me, the chip is a normal kind of a human body. For doctor, for me, the chip is a normal piece of silicon. I run some of the test on that silicon. I can find out what issues or what disease that chip has, and I can either fix that particular chip or I can make sure that those diseases will not appear in the next generation of the chip. So this is kind of an interesting thing which I thought of, and maybe this is what we discuss. So DFT engineer as a doctor for chips.
Great, Rohit. That was very interesting, and I think a lot of people will get a larger picture about what DFT is actually doing for the chip design services requirements, basically. Uh, so let's get into this whole thing about the whole building blocks from RTL to GDS2, and can you bring it down to the part and the steps which DFT goes through?
If we look at the macro view of the entire design cycle, the flow spans across two major worlds, pre-silicon and post-silicon. The RTL architecture gets designed, and at the same time, the DFT planning also happens. Then we take it through synthesis, and then we do the scan chain insertions, and then pattern generation happens. When we get the silicon fabricated, we take it on the tester and use those patterns and diagnose the issues. So inside the pre-silicon stage, the flow breaks into the four major steps. The first step is defining the DFT architecture. So when we look at the RTL, when we look at the design, The design might be using multiple components of, for example, flops will be there, for example, memories will be there, analog part will be there, IOs will be there. So depending on what and all components we are using, we have to define the DFT architecture. Once the DFT architecture is defined, the next step comes as a inserting that test structure in place. For example, if we have memories, we do MBIST insertion. We also have a lot of flops in the design. So basically, we do scan chain insertion. We use those flops, put them all together in a shift chain, and we make scan chains out of those all flops. The third step is using this structure which we have inserted. For that, we have to generate the pattern. Now the patterns gets generated using the EDA tools. So many times we use a lot of industry standard tools. We also have a method called ATPG, which is automatic test pattern generation, uh, which happens mostly when once we are done the scan chain insertion. We use the ATPG method to generate a lot of pattern for that. And the last step is applying all this pattern on silicon. So once we get the silicon, we take the silicon on the ATE on the tester, apply all those patterns which we have generated, and then make sure that all these defects, physical defects, are been getting identified. So we also work on the yield improvement and then making sure that the ppm is very less. We try to get good coverage on silicon. So these all activities we keep doing.
So, Rohit, you mentioned a lot of steps and processes. And for breaking it down, let's go to the basic fundamental concept, which you mentioned as scan chain. Uh, can you define what is it that goes into a scan chain process?
So, Rakesh, scan is a very basic element of the DFT architecture. So, when we do scan chain insertion, we are trying to get two major things out of it. One is controllability. We want to control the design the way we want, right? For that, uh, we have to push in the data inside the chip and make sure that the full design is under our control. And the second thing is, once you push in the inputs, once you given that inputs, the controls to the design, how the chip is behaving, how the design is behaving, you want to capture it and you want to observe that response, which is called observability. Now this is been achieved by converting all those sequential elements. So we have thousands and lakhs of flops in our design. So we basically put a extra additional mux, and that mux is required to make sure that when you are converting your design in the DFT mode, you are not disturbing your functionality. So basically we bypass the functionality, right, such a way that it is not disturbing the functionality. We use the muxes, put it in front of each and every flop, connect all the flops together, make a large, it's a huge chain which we try to make out of each and every flop in the design. So those all flops will become pseudo primary inputs. So basically they will be becoming our inputs through which we will be controlling the whole design, and they will also behave as pseudo primary outputs. Using them, we will be observing the behavior of the design. So this is what the whole scan chain insertion uh, gets us from the DFT point of view.
Fascinating, Rohit. So, one question which is coming into my mind is how do you switch between the functional mode and the DFT mode in this whole process?
So Rakesh, we have two different or two major modes under which the chip is operating, right? So one is a functional mode where you are applying all your functionality. You are using the functionality of the chip, making sure the application, whatever application you are designing your chip, is completely working and behaving as expected functionally. And the second mode is DFT mode or test mode. In the test mode, the functional behavior is deactivated. When I say deactivated, it is being used during DFT, but not the full functionality. Between flop to flop or between certain gates, you just use the minimal functionality and you come up with certain expectation from that functionality, and that behavior of the chip will help you to do the testing in your test mode. So we serially shifting the data as we discussed earlier. We control the chip, serially shifting the data, which are like vectors or the patterns, what you call it, execute or the cycles like clock pulses we provide, and let the combinational gate or let the functionality of the chip between flop to flop behave, and then next flop captures it, and then we can observe the results coming out of it.
Rohit, one question again, and is it that DFT has the capability of testing the logic gates, or it goes down to the transistor level? Do we have the capability of reaching down and identifying a defect in the minutest of the transistor level, or it's on the gate level?
So we implement the logic at the gate level, Rakesh, but the physical defects are occurring at the transistor level. Now the silicon chips are built using CMOS technology, so which is nothing but like lots of PMOS and NMOS transistors sitting together, coming up with the CMOS technology and manufacturing that chip using the CMOS technology. During manufacturing, microscopic variations in the process or the voltage or the temperature, which we call PVT corner, can happen. A lithography process can also cause some of the extra etching, or some kind of metal thickness can vary the results, or the uneven oxide layer whatever is there, like MOS means metal oxide, and semiconductor substrate, right? So in substrate also we have a lot of doping which we use. So this is a pure manufacturing process where the metals are used, the oxide layers are used, the doping is being used in the substrate. If an inverter, which is just a single CMOS transistor or a buffer, fails physically, it manifests as a logic failure. Because, for example, if the transistor is not behaving as a transistor, then the output of a transistor, which has to come out as an inverter or as a buffer, will not happen. And that is where the logical defects or the logical failures can occur, because our scan chains gives such deep visibility. If a pattern fails, our diagnostic software can trace the failures through the logic gates, and it can exactly pinpoint where which particular gate is not behaving properly, and that can correlate to the physical transistor that can cause this kind of defect in the gate.
So, Rohit, I understand that the scan chain builds the highway, and what are the next logical steps in the DFT process?
So once we have placed these scan chains in the design, then we use certain EDA tools. So basically, we have to generate the stream of bits to apply to the design, which will generate the output, which is also again in the binary format, and then you can measure it. So basically, applying the stimulus input side and measuring the output side, which is the response from the design, and these all will be calculated and put it together as a pattern, and the whole process we call it ATVG process, where it's an automatic test pattern generation, where the stimulus is being decided by the tool, because it all has to be done by the tool. It cannot be done by the human, because of the complexity, because of the massive number of flops or the big size of the scan chains and all. So we use the ATPG tool to apply the stimulus and measure the output and make sure that these patterns are getting generated using the tools, and then it will be used to find out the physical defects on the silicon.
So, these patterns are being generated through some logic, I would say, in terms of the DFT process which you put in. Uh, the curiosity or the fascination is, how do you detect a manufacturing challenge or a defect seeing these patterns?
So as we discussed, so the scan chains are used to shift in the bit by bit data. Now this bit by bit data will reach to each and every flop in the design, and between flop to flop you will have the logic gates. Now if these bits are reaching to each and every flop, because you know what are you giving to each and every flop, this flop will be applied to the logic between two flops, and the response will be captured in the next flop, which is already there in the design. So what happens is, you apply the input stimulus thinking that okay, there are AND gates, OR gates, lot of logic gates between the two flops, and then the output of that logic gates will be captured in the next flop, which you can again shift out, because you have already made the kind of a big shift register, right? So through which the input side you are applying the stimuluses, and on the output side you are measuring the expected output. And if the expected output is matching with what exactly you are expecting from each and every flop, then we can say yes, this particular part between flop to flop is working fine. And these all patterns are generated by using the ATPG tools. So if there is any miscompare, let's say for example, you applied the stimulus, and when you are measuring the output, or where when you are comparing the response from the design, you saw some flops are not matching, like you were expecting some different value and then flop is giving a another value. So that time you can say that this particular flop is not behaving, or the logic which is before that flop is not behaving as expected, which is what the physical failure or the defect can be. And this is how the defects can be flagged using these ATPG patterns on silicon.
What type of physical faults are you targeting with these patterns, Rohit?
So we use different mathematical fault models. So basically each and every defect on silicon is represented using the fault model in the DFT world. For example, your supply, right, the voltage source, VDD and VSS, if some pin gets connected to VDD, which is a constant 5 volt or 3 volt, then that particular net is going to continuously drive the active value 1. Now this is called a stuck at fault in the DFT terminology, where the particular wire or particular node got shorted or got connected to the VDD or VSS. Sometimes it is like open stuck, like where it just the wire got disconnected and it is just open. So those are all defects, physical defects, which can be represented the with the fault model called stuck at. Now some nodes are able to make the transition from 0 to 1 or 1 to 0, but they are slow in making this transition. So sometimes what happens is 0 to 1 or 1 to 0 transition is happening, but it is not happening at the required time. So just to give example, like if we have a system which is running at 1 gigahertz frequency, now 1 gigahertz means between flop to flop the transition, or from 0 to 1 or 1 to 0, you are expecting it to happen within 1 nanosecond, kind of a very short period of time. Now if that does not happen, then the whole chip cannot meet its own performance, or whatever it is designed for, making the things work at 1 gigahertz, it's not going to happen. So which is represented by the fault called transition fault or at speed fault. Now the thing which is happening between flop to flop, now there can be multiple paths, where some of the paths are critical, some of the paths are not critical. So we also have a model where we can represent those path related defects using the path delay fault. We have the current related faults, where the current either leaking, the leakage current is more, or the current which is running between the drain and source is like more than the expected, right? Because of that, now let's say for example you have the handheld devices, your mobile or your laptop, if it is driving too much of leakage current, or if it is driving too much of the active current, then it is going to drain out the battery. And because of, and all these are the physical defects. Now these are all happening on silicon. How do you find out? So we have a current measuring technique where you use the IDDQ patterns, which will help you to find out these kind of current related defects from the design. So our ultimate goal is to achieve the maximum fault coverage using the minimal number of patterns. This is what we achieve in DFT.
So this is basically what I see is that there will be a lot of millions of bits of data which will be fed into the scan chain process, and it could make it very lengthy in terms of the time taken and the complexities. So, from a manufacturability and a manufacturing cost per se, doesn't it increase this whole cost of manufacturing? And because the testing cost goes up?
Correct, Rakesh. So what happens is these all patterns, ultimately we are going to run them on the tester. Now these testers are very costly. Per second, or the cost of the tester per second is very high. Now the more you are holding the tester for testing the chip, is it's going to be more production cost for you. So the time taken on testing is a time for the production. So that is where the testers less hours on tester is always a good thing. So the manufacturing cost can skyrocket if you continue to hold the tester for a long time. Now uh, how do you optimize this pattern? How do you make sure the tester hours are reducing? And that is where the biggest challenge which comes to us as a DFT engineer. And then we have ways and means to make sure that you can reduce the test cost. so that ultimately in the competitive market you are able to sell your chip in a kind of a competitive rate.
So, well, you've addressed the cost element part of it. Now, seeing the complex, dense, and cutting edge chips which are coming on board, uh, the test time factor in terms of exploding. So, how do you control that factor? Because cost has been controlled. The time taken to test these chips is also a critical factor because time to market is very important. So, how do you do that?
So that is where exactly we have come up as a DFT engineer. We have come up with a technique called compression technique. So what we do is in the scan chain we shift in the lots of bits of data. Now the measure time which is taken on tester is shifting in data and shifting out the data. Now if we have the thousands and lakhs of flops sitting in one chain, then definitely it is going to increase the cost of testing it, because each and every bit by bit you have to shift in the data. What if you reduce the chain length? What if you cut the whole shift register into the multiple pieces? That way you reduce the number of shift requirement on tester, which is drastically reducing your tester time. Now these all can be achieved by using the compression logic. Now when I say the compression logic, there is a logic which is sitting at the input side and the output side. At the input side, we have a decompressor which will again expand the sequence of bits which we are pushing in from the input side. It will expand them such a way using the decompressor logic. Then each and every short chain, because now the big chain which you had earlier, which was like legs of flop, now you have cut them down and you have made them like short chains. So this decompressor logic is going to take the input, feed it into all the short chains, and then make the shift very fast. On the output side, all these short chains again need to get compressed and put them together. For that we use the compactor logic, and that will all come together. Compacted output will be given to the single output. So this is the compression technique what we use to make sure that the test time reduction happens effectively and we still achieve the goal, or the ultimate goal for us to do the proper testing, have the proper quality of the chip, and have the reliable chip. So this is still can be achieved.
So, with the compression logic applied into the modern SOC testing, it has become possible for it to become scalable.
Exactly, Rakesh. It bridges the gap between the massive internal design complexity and the expensive external tester resources.
Thank you, Rohit, for a lovely and incredible lowdown today. And I hope the listeners would have had a good insight about the subject.
It was my pleasure. Thank you very much, Rakesh.
Let's recap what we covered today: the end to end pre silicon and post silicon DFT flow, scan insertion, and how converting standard flip flops into scannable elements give us controllability and observability right down to the CMOS transistor level, ATPG, and how fault models like stuck at and transition faults are used to catch physical defects. And finally, modern test compression techniques that keep test times and production costs under control.